Hi physical science students, this video is intended to help you with TSW number, what is it, number 6, TSW number 6 of Unit 9. This TSW states that you need to be able to state evidence for both the particle and wave model of light. To kind of explain the nature of light at both as a particle and a wave. And there's a lot to be said in here. I hope this video will not be too long. There has been a debate about whether light is a particle or a wave that has been going on for thousands of years, and it was only after the kind of when the scientific method was developed that scientists started to actually perform experiments that were intended to really discover whether light is a wave or a particle. And if it is a wave, then wave of what? Because we know that there has to be something waving, and we know that light can travel through vacuum where there's nothing there. So if light is a wave, it is some kind of special wave. So what is it that is waving in it? And in the early 1800s, at the beginning of 19th century, Thomas Young, a brilliant British man, he showed an experiment that at that moment or that time thought to have proven, definitely proven, kind of that light is a wave, and the debate was over. He sent light through two tiny narrow slits, and he observed the pattern of light at the back on the wall. And the pattern kind of showed not two narrow bands of light passing through the two slits, but it showed a pattern of dark, bright, dark, bright, dark, bright bands, many, many dark and bright bands. And this could only be if the light passing through the two narrow slits diffracts. Remember we talked about diffraction. It kind of starts bending behind the two slits, and the two waves that are caused by going through the two slits will interfere with each other. Sometimes they will interfere constructively, sometimes destructively, and it will form this kind of a pattern of bright and dark bands. And you can actually try this yourself, not the double slit experiment, but you can kind of create an interference pattern of light if you hold two fingers like this, so that there is a tiny space in between of your two fingers, and you point them at a source of light, and then you bring your fingers together so that there is only a tiny, tiny narrow slit. And at a certain moment you will start seeing these horizontal lines of dark and bright, which are caused by light interfering with each other constructively and destructively as it goes through this tiny, tiny narrow slit. So this is evidence for wave nature of light, that light is a wave, or has a, that something is waving in light. Then later on, by studying electricity and kind of putting the two things together, it was discovered that these waves are waves of electric and magnetic field. Again, we haven't discussed what electric and magnetic field is yet. But it's sort of a self-propagating electromagnetic wave. We call it an electromagnetic wave. And they thought that the puzzle, the secret, was solved. But then at the beginning of 20th century, there was a phenomena that really puzzled the scientists. No one could explain the phenomena. It definitely could not be explained if light was a wave. It was called the photoelectric effect. And photoelectric effect basically is an ejection of electrons from a metal or from some material just because light is shined on the material. So in this electroscope, where we can show the charge of this ball in here, if we shine ultraviolet light in here, we'll start seeing that electrons are ejected from here, and the electroscope starts showing that the sphere is charged. And it is the details of this experiment, not the fact that the electrons are ejected, because in theory that could be done by a wave. So a wave could come and hit the sphere and eject the electrons. But it is the details of this experiment which we don't have time, or we don't deal with the details here in physical science. But those details show definitely that light is a stream of particles, and we call those particles photons. And it was the explanation of this photoelectric effect that actually earned Albert Einstein his Nobel Prize, which he received, I believe, in 1921, because he was able to explain photoelectric effect. Just to kind of give you an idea of why it can be done by a wave. Imagine a beach, and it's a dirty beach. It has all of these plastic bottles on it, and a wave comes at the beach and hits the plastic bottles, and you would expect that all along the wave, as the wave hits the beach, the bottles would be moved a little bit up the beach. This is not what we see with light hitting a metal plate. If it arrives as a wave, then definitely the energy of the wave does not move all of the electrons a little bit. And you would be very surprised if you saw this, a wave coming to a beach, and that out of those many plastic bottles, instead of moving them all of them a little bit, the wave chooses one plastic bottle and shoots it 10 kilometers inland. This is the same thing, the equivalent that we see with light hitting a metal sphere, a metal plate or a sphere or a piece of metal. The wave arrives at the metal and picks one electron and shoots it totally out of the metal. This cannot be explained if light is a wave, but only if light is a stream of tiny particles, which we call photons. So we have evidence for both. We have the interference of light as it passes through narrow slits, which is evidence for light being a wave. If you shoot bullets through a narrow slit, you wouldn't see the bullets interfering with each other. Then we have this evidence for the particle model of light with the photoelectric effect. So kind of two phenomena which are sort of showing us two sides of the same coin. Kind of when you touch an elephant, depending on, blindfolded, depending on where you touch it, you will describe it differently. And so maybe it is that we don't exactly know what light is, but we see that sometimes it behaves as a wave and sometimes it behaves as a particle. So we don't think of it as either a wave or a particle. It has this dual nature.